Welcome to the 2 Degree of Freedom Inverted Pendulum Project movie presentation. This project has been completed by a group of 3 students taking the Automatic Control Project course at KTH EES School in Stockholm. The goal of this project was to stabilize this inverted pendulum. The key to stabilization is controlling the pendulum base angles to 0 through movement of the pendulum base. This is the 2 Degree of Freedom inverted pendulum process. It consists of a control computer, a terminal board for easy interface between the computer and the rest of the process, 2 separate power modules, and the inverted pendulum setup. The setup itself is made up of several components. First of all, the pendulum. It is a 30 cm long uniform rod, which base is connected to a 2 Degree of Freedom gimbal. As you can see here, the pendulum is free to tilt in any direction. This tilt can be measured using 2 encoders at the pendulum base. The gimbal is in turn placed on the end effector of the arm system. The arm system translates rotational movement into XY movement of the pendulum base. The 2 plants seen here are called servo plants, and their main component is the electrical motor that through a gearbox turns the load shaft. The servo plant also includes a potentiometer to sense the position of the load shaft. The program used for implementation is LabVIEW, and this is the front panel of that implementation. When the program is started, the figure in the upper left corner of the screen shows the current position of the link arms. Here, the link arms are being physically moved. To stabilize the pendulum itself must first be held in an approximately upright position. The Stabilize Pendulum button on the front panel can then be pressed to make the controller take over. For this application, the system has been assumed to be decoupled. What that assumption means is that the rotation of one of the servo plant load shafts only creates movement in one direction at the pendulum base. This is an assumption that is absolutely true only when the pendulum base is at its 0 positions where all the angles between the link arms are 90 degrees. However, it is a fair approximation whenever the pendulum is close to that position. Furthermore, the system has been linearized around a 0 state, where the pendulum base is at its 0 position and the pendulum angles are 0. The control strategy used here is LQ control, and since the velocities of both the pendulum angles and the load shaft angles can't be measured, a Kalman filter has been implemented to estimate those states. Substantial work has been put into reducing these oscillations that can be seen here mainly in the Y direction. The final conclusion is that these oscillations are related to a substantial backlash in the left servo plant, the fact that the encoder cables pull on the gimbal and other nonlinearities not taken into account. It is possible for the user to decide which point in the XY plane to stabilize the pendulum around. Here it is shown what it looks like when the user changes the base reference position from 0 to 4 for both the X and the Y axis. As can be seen here, the performance is still quite good. This is thanks to 2 non-linear components that are a part of the implementation. First of all, the feedback of the pendulum base position is done through the complete non-linear trigonometric equations relating the load shaft angles to the base position. Secondly, the fact that the gimbal rotates around the Z-axis when the link arms extend away from the 0 position has been taken into account. This improved the performance drastically. The system is robust against disturbances of different kinds, as can be seen here when the pendulum is hit with a pen. Even when the pendulum is away from its 0 position, it is capable of attenuating disturbances. There is, however, a limit to how far the link arms can extend. Therefore, the pendulum is extra sensitive to disturbances when it's far away from its center point. Finally, Tintin's dog Milou is taking a ride on the pendulum to illustrate that the system can handle errors in the model. Note how Milou shifts the center position of the pendulum mass in a way that makes the system stabilize the pendulum at a slight angle. That concludes this video presentation. Hopefully it has been to your liking, and thank you very much for watching.